Welcome. You've stepped into the world of sleepy knowledge, a place for quiet curiosity. Tonight, we'll slow down and unfold how information moves between our world and the one just beyond it. But before we begin, I'm always curious, where in the world are you listening from tonight? And if you find yourself drawn to explorations like this, you're welcome to subscribe. Right now, above your head, there are signals passing through the ceiling of your home, through the roof, through the clouds, through the upper atmosphere, up into the dark, cold silence of space, and back again. In the time it takes you to finish this sentence, something invisible has made a round trip of thousands of miles. You didn't feel it. You never do. But it happened. Now, prepare for one of the most quietly extraordinary stories in the history of human civilization. A story about how we learned to talk to machines floating in the void, and how those machines learned to talk back. Let's begin with something simple. You are lying down right now. Maybe the lights are off or low. Maybe there's a phone on your nightstand. Maybe there's a weather app on that phone. And earlier today, you glanced at it, saw there was a chance of rain, and decided to bring a jacket. You didn't think twice about it. But that forecast, that small, unremarkable piece of information, traveled somewhere extraordinary before it arrived in your hand. It was gathered by instruments on a spacecraft orbiting the Earth at roughly 35,800 kilometers above the surface. It was compressed into a signal. That signal was beamed downward, through space, through the atmosphere, through a receiving antenna, processed, interpreted, packaged, and sent to a server, which sent it to your phone, which decoded it and rendered it as a little cloud icon with a raindrop. The whole journey took fractions of a second, and you just glanced at it and moved on. That is the world we live in. That is the miracle we have normalized. So tonight, let's unnormalize it. Let's take that invisible journey and stretch it out. Let's look at every stage, every decision, every piece of physics and engineering that makes it possible for a machine the size of a refrigerator or sometimes a school bus to float in the vacuum of space, 36,000 kilometers above your head, and have a conversation with the ground. Because the story of satellite communication is not just a technical story. It is a deeply human story. It is a story about longing, about our desire to see farther, to reach farther, to know more. It's a story about a time when the idea of sending a signal to space seemed not just impossible, but vaguely insane. And it's a story that is unfolding right now, above you, in the dark. Let's start with a question. How do you send a message somewhere you cannot go? Think about that for a moment. Not in the context of space, but in general. Throughout history, humans have always faced this problem. You have information. You need to get it somewhere. But you can't carry it yourself. The earliest solutions were physical. You sent a runner. You sent a rider. You lit a fire on a hilltop and hoped someone was watching from the next hilltop. Then came something revolutionary, the telegraph. The idea that you could encode language as a pattern of electrical pulses and send it down a wire, in an instant, over a distance that no runner could cover in days. The telegraph didn't just change communication, it changed how humans understood time. The concept of something happening, somewhere else, simultaneously, was new, profoundly new. Then came the telephone. Then radio. And with radio, humanity crossed a threshold that, if you think about it carefully, is rather astonishing. With radio, you could send information through the air, not through a wire, not through a physical medium at all, through nothing, through the invisible fabric of space itself. James Clerk Maxwell had predicted this in the 1860s. His equations, which Einstein famously called the most important event in physics since Newton, described the existence of electromagnetic waves, waves that could propagate through a vacuum, waves that traveled at the speed of light, because light itself is one of them. Heinrich Hertz confirmed it experimentally in 1887, and Guglielmo Marconi, that strange and stubborn Italian inventor, turned it into a technology. By 1901, Marconi had done something that most scientists thought was physically impossible. He transmitted a radio signal across the Atlantic Ocean, from Cornwall in England to Newfoundland in Canada. People were not just impressed, they were disturbed, because the Earth is curved. Radio waves, everyone assumed, traveled in straight lines. A straight line from England to Canada would pass right through the body of the Earth. The signal should have simply gone into the ground. But it didn't. It bounced off a layer of the upper atmosphere, a band of charged particles called the ionosphere, and curved around the planet like a whisper traveling around the inside of a dome. Marconi didn't entirely understand why it worked. He just knew that it did, and that tension between doing something and understanding it runs like a thread through the entire history of this field. Now, let's jump forward. It's 1945. The war is ending. A young radar engineer and science fiction writer named Arthur C. Clarke is sitting in London, writing a letter to a technical journal called Wireless World. The letter is titled Extraterrestrial Relays. In it, Clarke describes something that does not yet exist. He describes a satellite, an artificial object placed in orbit around the Earth at a very specific altitude. An altitude where the orbital period, the time it takes to go around the planet once, is exactly 24 hours, which is the same as the Earth's rotation period. Which means, from the perspective of someone standing on the ground, the satellite never moves. It just hangs there, fixed in the sky, like an invisible radio tower 36,000 kilometers tall. Clarke proposed that 3 such satellites placed at equal intervals around this orbit, what we now call geostationary orbit, could relay radio signals to any point on Earth. Global communication, achieved with 3 objects floating in space. He wasn't just describing a product. He was describing a new architecture for human civilization, a way of connecting the entire surface of the planet with a single system overhead. Most people read the letter and filed it away as clever speculation. A few took notes 12 years later, on October 4th, 1957. The Soviet Union launched a small, polished metal sphere into orbit. It weighed 83 kilograms. It was about the size of a beach ball. It had 4 radio antennas trailing behind it like the legs of a metal insect, and every 96 minutes it circled the Earth, broadcasting a simple radio signal. A steady beep 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 beep, beep on 2 frequencies, 20.005 and 40.002 megahertz. The signal meant nothing. It carried no data, no voice, no information at all. It just existed. It said, I am here. I am here. I am here. I am here. Sputnik, amateur radio operators around the world, picked up the signal. Families gathered around radios in living rooms and kitchens. Scientists rushed to their equipment. Military planners stared at maps. What they heard was not a threat exactly. not a declaration of war. It was something subtler and, in some ways, more unsettling. It was proof that the sky was no longer a ceiling, that the space above the atmosphere was reachable, that human-made objects could exist there, in orbit, indefinitely, that the high ground, the highest possible ground, was now contested territory, and that signals could come from it. But here is where the story gets genuinely interesting and genuinely strange, because the challenge of communicating with a satellite is not simply a matter of pointing an antenna upward and shouting loudly. Space is almost unimaginably hostile to communication. Let's think about why. When you speak to someone in the next room, the sound waves from your voice travel a few meters. By the time they reach the other person's ears, they've barely lost any energy at all. When you shout across a field, your voice has to travel farther. The sound spreads out in all directions. By the time it reaches the other end of the field, it's a fraction of its original intensity. This is called the inverse square law, and it is ruthless. The intensity of a signal, any signal, decreases with the square of the distance from its source. Double the distance, and the signal becomes 4 times weaker. Triple the distance, 9 times weaker. Triple the distance, 9 times weaker. 10 times the distance, 100 times weaker. Now, take that principle and apply it to a distance of 36,000 kilometers. A signal sent from a satellite in geostationary orbit must travel that distance before it even enters the atmosphere. By the time it reaches the ground, it is spread out over an area millions of times larger than when it left the antenna. The power that arrives at your receiver, your dish, your phone, your GPS unit, is not just weaker. It is almost incomprehensibly weaker. We are talking about signal levels measured in picowatts. That is trillionths of a watt. To put that in perspective, a single AA battery contains enough energy to power the signal from one GPS satellite for roughly 300 million years. The signal that reaches your phone from that satellite is so faint that it contains less energy than a single photon of visible light, and yet, your GPS unit can locate you to within a few meters. This is not an accident. This is engineering, precise, patient, painstaking engineering. Applied to one of the most fundamental challenges in physics, let's talk about frequency. Not all radio waves are created equal. The electromagnetic spectrum is vast. It stretches from extremely low-frequency radio waves with wavelengths longer than a continent, all the way up through visible light, X-rays and gamma rays with wavelengths smaller than an atom. For satellite communication, the frequencies that matter most sit in a particular band, the microwave range, roughly between 1 and 40 gigahertz. Why microwaves? Because at lower frequencies, the atmosphere starts to reflect and absorb signals. The ionosphere, that layer of charged particles that Marconi's signal bounced off, acts like a mirror for low-frequency radio waves, which is great for broadcasting around the planet, but terrible for communicating with anything above the ionosphere. You can't get a low-frequency signal through the ionosphere to a satellite. It just bounces back. Microwaves, on the other hand, pass through the ionosphere as if it isn't there. But they introduce their own problems. They can be absorbed by rain, a phenomenon called rain fade, which is why your satellite TV sometimes cuts out during a heavy storm. They can be blocked by buildings, trees, mountains. They travel in essentially straight lines with almost no ability to bend around obstacles, which is why satellite dishes need to be pointed precisely at the sky with a clear line of sight. The signal doesn't meander. It doesn't go around corners. It demands a direct, unobstructed path between the antenna on the ground and the spacecraft in orbit. Within the microwave range, satellite engineers work with several specific bands. You'll hear these terms if you ever look into the industry: L-band, S-band, C-band, Ku-band, K-band. Each is a range of frequencies with its own characteristics. Trade-offs between bandwidth, beam size, susceptibility to weather, and the physical size of the equipment needed. C-band, roughly 4 to 8 gigahertz, was the workhorse of early satellite TV. It requires large dishes, the kind you used to see in rural yards, several meters across. Big, unwieldy, but extremely reliable in bad weather. Ku-band, 12 to 18 gigahertz, allowed smaller dishes, which is why direct-to-home satellite TV became practical. The little oval dish on the side of a house. But Ku-band is more susceptible to rain fade. K-band, 26.5 to 40 gigahertz, offers very high bandwidths. It's what many modern high-speed satellite internet systems use. It can carry enormous amounts of data. But it requires precise pointing and is quite sensitive to atmospheric conditions. And then there's GPS, which operates in L-band, down around 1.2 to 1.6 gigahertz. Lower frequency, more tolerant of atmospheric conditions. Small enough in wavelength to use compact antennas. Ideal for a system that needs to work in your car, in your pocket, in the middle of a forest or a desert. Every frequency choice is a negotiation. You are always trading something for something else. Now, let's talk about the most important single piece of hardware in this entire system: the antenna. An antenna is, in its essence, a remarkably simple thing. It is a conductor, a piece of metal shaped in a way that allows it to either radiate energy outward as radio waves or to receive radio waves and convert them back into electrical signals. That's it. A piece of metal shaped correctly. And yet, the design of antennas is one of the deepest fields in engineering. The shape, size, orientation, and material of an antenna determine its directionality, how focused its beam is, how efficiently it transmits and receives, what frequency range it handles. A simple dipole antenna. Two rods pointing in opposite directions, like a capital T without the vertical stroke, radiates energy in all directions perpendicular to its axis. Like a donut of radio energy. Good for broadcasting, bad for focusing power in a particular direction. For satellite communication, where the signal has already traveled tens of thousands of kilometers and arrived as a whisper, you need to focus every available watt of energy into the narrowest possible beam. The solution is the parabolic dish antenna. You know what a parabola is? The smooth, curved shape of a satellite dish. This shape has a remarkable geometric property. Any signal arriving parallel to the axis of the parabola, coming from directly in front of it, is reflected toward a single point called the focus. A receiver positioned at the focus collects energy from the entire surface of the dish and concentrates it into a single point. The larger the dish, the more energy it collects, and the more focused the beam it can transmit. This is why the dishes used by deep space communication networks, facilities like NASA's Deep Space Network at Goldstone in the Californian desert, or at Canberra or Madrid, are enormous. Some are 70 meters across, nearly the height of a 20-story building. To communicate with a spacecraft a billion kilometers away, with Voyager 1 now beyond the boundary of our solar system, you need the largest ears you can build. And you need extraordinary patience. A signal from Voyager 1 takes more than 22 hours to reach Earth at the speed of light. When you press send, you wait almost a day for any acknowledgement that the message arrived. The satellites we use every day, the ones managing your phone calls and GPS and weather data, are not quite that far away. But the principles are the same, and there is something I want to linger on here, before we move into the mechanics of how data actually moves. There is a kind of poetry in the physics of antenna design. The reason a parabolic dish works, the reason it can gather the faintest whispers from the sky and concentrate them into something useful, is because of a simple, beautiful truth about geometry, that a parabola converts parallel lines into a single point, parallel lines from infinity. The signal from a satellite 36,000 kilometers away arrives at your dish not as a whisper from nearby, but as a breath from the horizon. Parallel, uniform, barely distinguishable from nothing. And the dish gathers it, shapes it, turns it into something legible. There is something almost meditative about that image. The dish, still and silent in the dark, waiting, listening for a voice so quiet it borders on imaginary. Let's talk about language. Not human language, machine language. The language that exists between a satellite and the ground. A language made of mathematics and physics, constructed specifically to survive a journey through the vacuum of space. Before a satellite can send you any information, a phone call, a weather image, a navigation fix, that information has to be transformed, converted, translated from its original form into something that can be carried by a radio wave. This process is called modulation, and it is, when you think about it, one of the most elegant ideas in all of engineering. Here's the core concept. A radio wave is, at its most basic, a simple, repetitive oscillation. A sine wave, up, down, repeating at a fixed frequency. It carries no information in itself. It's just there. A steady hum in the electromagnetic field. To make it carry information, you need to vary something about it. You can vary its amplitude, the height of the wave, make it taller to represent one value, shorter to represent another. This is amplitude modulation, AM radio. You can vary its frequency, how fast it oscillates. Slightly faster means one thing, slightly slower means another. This is frequency modulation, FM radio. And this is what most digital systems do. You can vary its phase, the timing of the wave. You can shift the wave slightly earlier or later in its cycle to encode information. This is phase modulation, and in its most common form, called BPSK, binary phase shift keying. It is almost beautiful in its simplicity. A phase shift of 0 degrees represents a binary 1. A phase shift of 180 degrees, a complete flip of the wave, represents a binary 0. With this single, elegant trick, 2 mirror image waves, you can encode every piece of information that has ever traveled from a satellite to a receiver on Earth. But of course, we want to send more than just ones and zeros, or rather, we want to send them faster, more efficiently. So engineers developed more sophisticated variants. QPSK, quadrature phase shift keying, uses 4 phase positions instead of 2, encoding 2 bits per symbol instead of 1. 8PSK uses 8 positions, encoding 3 bits. 16COM, quadrature amplitude modulation, combines phase and amplitude changes to encode 4 bits per symbol. With each step up, you transmit more data for the same amount of bandwidth. But there's a catch. There's always a catch. The more complex the modulation scheme, the more data it crams into each symbol, the harder it becomes to distinguish one symbol from another in the presence of noise. And space is full of noise. Thermal noise, random electromagnetic fluctuations caused by the simple fact that matter has temperature. Interference from the sun, from other satellites, from human-made electronics on the ground. The noise floor of the universe itself. When your signal arrives at the receiver as a whisper, trillions of times weaker than when it left, the noise starts to become as loud as the signal. And at that point, telling the difference between a phase shift of 45 degrees and 90 degrees becomes very, very hard. So you choose your modulation based on the quality of your link. A GPS satellite, which needs to work in a pocket, uses the simplest, most robust modulation it can. A high-throughput satellite delivering broadband internet to a fixed dish, where more precise, more powerful equipment is available, can use the more complex schemes. This is called link budget analysis. And it is essentially a careful accounting of every watt, every decibel, every source of gain and loss in the system, to determine what modulation scheme the link can support. Link budget. I love that term. It implies exactly what it means. You have a budget. You can spend it wisely, or you can overdraw it. And if you overdraw it, the signal falls into the noise, and the conversation ends. Now, once you've modulated your signal, once your data is riding on a radio wave, you transmit it. But raw transmission is not enough, because in a real communication link, errors happen. Bits get flipped. A 1 becomes a 0. A precisely timed phase shift arrives at the wrong angle. Not through any failure of the equipment, simply because of the physics. Because noise is real, and it is everywhere. And in satellite communication, where the signal has crossed tens of thousands of kilometers, the error rate can be significant. This is why every satellite communication system includes something called forward error correction, FEEC. It is, in some ways, the unsung hero of modern digital communications. The idea is elegant. Before you transmit your data, you add carefully calculated redundancy to it. Extra bits. Not carrying new information, but carrying a mathematically precise summary of the information they accompany. A kind of fingerprint. When the receiver gets the signal, even if some bits have been corrupted by noise, it can use that mathematical fingerprint to detect and correct the errors. To reconstruct the original data, even from a damaged copy. The most powerful modern FEC schemes, things called turbo codes and LDPC codes, low-density parity check codes, can recover the original data from signals so noisy that the error rate before correction is nearly 50%. Nearly random. They can extract signal from noise so thoroughly that they come within a tiny fraction of the theoretical limit, the Shannon limit, the mathematical ceiling on how much information can be reliably carried through a noisy channel. A limit derived by Claude Shannon in a landmark 1948 paper that essentially invented the field of information theory. Shannon's paper was so far ahead of its time that when he first showed it to colleagues, several of them quietly assumed he had made an error somewhere. It seemed too clean, too complete. He hadn't made an error. Let's talk about one of the most important concepts in satellite communication. A concept so fundamental that it underlies almost every element of how these systems are designed. The concept is called latency. Latency is delay. The time it takes for a signal to travel from one point to another. For a geostationary satellite, sitting at 35,786 kilometers above the equator, the one-way travel time for a signal at the speed of light is approximately 240 milliseconds, nearly a quarter of a second. For a round trip, signal goes up, signal comes back. That's roughly 480 milliseconds. Half a second. In human terms, half a second doesn't sound like much. But in communication terms, it is enormous. Think about a phone call through a geostationary satellite. Every time you speak, the other person doesn't hear you for half a second. Every time they respond, you don't hear them for half a second. This is why satellite phone calls have always had that distinctive, slightly eerie quality. The unnatural silence after you speak, while your words are traveling up to space and back down to the other side of the world. For casual conversation, it's tolerable. For online gaming, where milliseconds matter, it's completely unworkable. For financial trading, where high-frequency algorithms make decisions in microseconds, geostationary latency is not just inconvenient, it's prohibitive. This is the fundamental tension at the heart of geostationary satellite design. The same altitude that makes the satellite appear stationary, the same altitude that allows a single satellite to see an enormous area of the Earth, serving millions of users simultaneously, is the altitude that guarantees that half-second delay. You cannot have both. You cannot be stationary and close at the same time, unless you rethink the geometry entirely. What if, instead of one satellite high up, you put many satellites low down? This is the idea behind low Earth orbit, or LEO. Satellites in LEO orbit at altitudes typically between 500 and 2,000 kilometers. At these altitudes, the signal travel time drops to between 2 and 10 milliseconds, barely perceptible to a human. Quite workable for gaming, trading, real-time applications. But here's the problem. At 500 kilometers, a satellite is not stationary relative to the ground. It is hurtling overhead at roughly 7.5 kilometers per second. It rises above the horizon, arcs across the sky, and sets again in perhaps 10 minutes. Any given point on the Earth is only visible to a LEO satellite for a brief window. So if you want continuous coverage, if you want your phone to always have a satellite overhead, you need many satellites. Not 3, like Clark's geostationary vision. You need hundreds or thousands. The first practical EO satellite phone system, Iridium, launched in the late 1990s with 66 satellites. It was an engineering achievement of staggering ambition, and it nearly destroyed the company that built it. The cost of launching and maintaining 66 spacecraft in precisely coordinated orbits proved so enormous that Iridium filed for the largest bankruptcy in telecommunications history. The original satellites were nearly deorbited, burned up in the atmosphere. The last moment, a consortium of investors, including the U.S. Department of Defense, purchased the system for roughly $25 million, a tiny fraction of the $5 billion it cost to build. And today, Iridium is profitable. The technology eventually found its market: remote workers, maritime operators, military applications, and the system was upgraded and expanded. But the lesson of original Iridium haunted the industry for a decade, until someone decided to try again, at a scale that made Iridium look modest. The story of modern LEO constellations is one of the most dramatic stories in the history of technology. We'll come back to it in detail later. But let me plant a single image in your mind right now. At the time of this writing, above you, right now, there are roughly 5,000 Starlink satellites in orbit. By the end of the decade, SpaceX has filed to launch over 40,000. The geostationary belt, the ring of satellites at 36,000 kilometers, has perhaps 500 active satellites in it. Total. The LEO shells being built today are an entirely different order of magnitude, and the communication systems linking them to the ground and to each other represent a fundamental rethinking of how satellite communication works. But before we get there, I want to go back down to Earth for a moment, literally, because the satellite is only half the story. The ground is where the magic gets translated. Every satellite in orbit is, in some sense, a relay station. It receives signals from the ground. It amplifies or processes them, and it transmits them back, either to another point on the ground or to another spacecraft. The facilities on the ground that make this possible are called ground stations, or Earth stations, or teleports, or in the context of navigation systems, control segments. They come in many forms. Some are vast, campus-like facilities in remote desert locations, chosen specifically because they are away from sources of radio interference, under clear skies with unobstructed views of large areas of sky. Others are modest installations on rooftops or hillsides, and increasingly, as technology has miniaturized, some are portable units that can be set up almost anywhere, but all of them share a common purpose. They are the bridges, the points of contact between the invisible world above and the tangible infrastructure below. Let's walk through what a typical ground station actually does. A large satellite Earth station, the kind used for broadcast television or telecommunications, typically consists of a number of major subsystems. First, the antenna, often a large parabolic dish, oriented toward a specific satellite or arc of the sky. In some facilities, dozens of dishes of various sizes are clustered together, each pointed at a different satellite in a different orbital slot. The dish is mounted on a motorized tracking system. Even geostationary satellites, which appear stationary, drift slightly due to the gravitational influence of the Moon and Sun and the slight asymmetries of the Earth's shape. A tracking system compensates for this drift, keeping the antenna pointed precisely at the satellite at all times. Attached to the dish, at the focus point, where the parabola concentrates incoming energy, is a device called a feed horn. The feed horn collects the focused energy and channels it to the next component. That next component is a low-noise block-down converter, an LNB. It does two things. It amplifies the received signal, boosting it from picowatts to milliwatts, making it workable. And it shifts the frequency downward, from the high-frequency microwave signal that came from the satellite to a lower frequency that can be carried through ordinary coaxial cable to the equipment inside the building. This is why you can run a satellite signal from the dish on your roof to a receiver inside using ordinary cable. The LNB has already done the hard work of amplifying and converting it. Inside the building, the signal goes through further processing. Demodulation, the reverse of modulation, extracting the digital data from the radio wave. Error correction, using those mathematical fingerprints to detect and fix transmission errors. Decryption, if the signal is encrypted, decoding from whatever compression format was used. And finally, the data arrives as something humans or machines can use. A stream of video, a voice call, a weather image, a navigation signal. I want to take a moment to talk about a specific kind of ground station that almost never gets mentioned in popular accounts of satellite communication, but which is, in many ways, the most important of all. The Tracking, Telemetry, and Command Station, TT&C. Every satellite, from the moment it's launched to the moment it falls silent, must be monitored. It must be tracked, precisely located in its orbit. Its internal systems must be measured and reported back to the ground. Temperatures, voltages, fuel levels, attitude, every parameter that describes its health and status. This is telemetry, and it must be commanded. Instructions must be sent to it. Adjust your orbit. Point your antenna this way. Increase power to this subsystem. Switch to the backup transponder. This is command. TT&C is the nervous system of a satellite program. Without it, a satellite is a beautiful, expensive piece of hardware drifting silently through space, uncontrolled and unreachable. The engineers who run TT&C stations are, in a very real sense, the caretakers of machines they will never touch. They will never climb up and change a faulty component. They will never turn it off and on again. When something goes wrong, and something always eventually does, they must diagnose the problem, design a solution, and implement it, all through radio waves. There is something profoundly moving about that relationship. The engineer in a windowless room at 3 a.m., staring at telemetry data streaming in from a spacecraft 36,000 kilometers away, trying to understand why a voltage reading has drifted by a fraction of a volt, trying to coax a machine back to health. Through the medium of electromagnetic pulses, the machine cannot feel their concern, but the engineer's concern is real. Let's talk about something that often gets taken for granted: the question of who controls what and how. A communications satellite, particularly a commercial one, may serve thousands of different customers: television broadcasters, telephone companies, internet service providers, government agencies. Each customer needs to use a portion of the satellite's capacity, its bandwidth, its power, its time. Managing this is, on one level, an engineering problem. On another level, it's a logistical and commercial puzzle of considerable complexity. The basic division of satellite capacity happens along two axes. Frequency, how much of the radio spectrum each user gets. This is divided into channels, or transponders. A typical commercial geostationary satellite might have 20 to 50 transponders, each occupying a specific chunk of frequency bandwidths, maybe 36 megahertz wide. Each transponder can be leased to a different customer. Time. Which user gets to transmit when? When many small terminals all share the same frequency band to communicate with a single satellite, as in a very small aperture terminal network, a VSAT network, they must take turns. This scheduling of transmissions across multiple users is called multiple access, and there are several ways to do it. Frequency division multiple access, FDMA. Give each user a different subfrequency within the band. They all transmit simultaneously, but at different frequencies. Time division multiple access, TDMA. Give each user a specific time slot. They take turns, each user bursting their data during their assigned moment. Code division multiple access, CDMA. Let everyone transmit simultaneously on the same frequency, but encode each user's data with a unique mathematical code that allows receivers to separate them even when they overlap. GPS actually uses a variant of CDMA. Every GPS satellite transmits on the same frequency, but each satellite uses a different spreading code, a different mathematical pattern. Your GPS receiver knows all the codes and uses them to pick each satellite's signal out from the shared frequency, like picking out individual voices in a crowded room. I want to step back from the technical detail for a moment, because I think there's something important to absorb here. The world of satellite communication is a world of extraordinary invisible precision. Signals measured in trillionths of a watt. Frequencies measured to parts per billion. Orbits calculated to centimeters. Error correction schemes that touch the mathematical limits of possibility. And all of this invisible architecture is in service of a fundamentally human impulse. The impulse to not be alone. The impulse to reach someone. To know something. To see somewhere you cannot go. When a ship is in the middle of the Pacific Ocean, thousands of miles from any coast, and a sailor calls home. That conversation happens because a signal travels up through 36,000 kilometers of space and back down. It happens because engineers spent decades working out how to make something this fragile, this reliable. The sailor doesn't think about any of that. The sailor is thinking about home. And that is exactly as it should be. We've talked about geostationary orbit and low Earth orbit, but the sky between the surface and deep space is more populated and more varied than that. Let me walk you through the orbital families, the zones, the neighborhoods that different types of satellites inhabit, and why they chose those neighborhoods. First, low Earth orbit. LEO. Between roughly 160 and 2,000 kilometers above the surface, the lower bound is determined by the atmosphere. Below 160 kilometers, the residual atmosphere is thick enough to generate significant drag. A satellite at 150 kilometers would deorbit, spiral back into the atmosphere in a matter of days. At 400 kilometers, the altitude of the International Space Station, a satellite will stay in orbit for years, but it still needs periodic reboost to compensate for atmospheric drag. At 550 kilometers, where many of the Starlink satellites operate, orbital lifetime without propulsion would be roughly 5 to 8 years before drag brings them down. LEO is the busiest zone in near-Earth space. It's where Earth observation satellites operate, capturing images and radar data of the surface. It's where scientific missions go. It's where crewed space stations have always been built. And now, it is where the new generation of broadband constellations lives. The advantage of LEO for communication is primarily that latency number, 20 to 40 milliseconds round trip, close enough to terrestrial internet speeds that most applications work seamlessly. The challenge, as we discussed, is coverage. A single EO satellite at 550 kilometers has a footprint on the ground of perhaps 1,000 kilometers in diameter. To cover the entire Earth continuously, you need the orbital equivalent of a tiled floor. Many satellites in many orbital planes arranged so that their footprints overlap, and at least one satellite is always in view from any point on the surface. For Starlink, with its ambitious plans for tens of thousands of satellites, this means something like a spherical shell of spacecraft surrounding the planet, all communicating with the ground below and with each other in an orchestrated, constantly shifting network. Next, medium Earth orbit, MEO. Between roughly 2,000 and 35,000 kilometers, this is the realm of navigation satellites. GPS, the American system, operates at about 20,200 kilometers. Russia's GLONASS at about 19,100 kilometers. The European Galileo system at about 23,200 kilometers. China's Beidou at multiple altitudes, including MEO. At 20,000 kilometers, the orbital period is about 12 hours. So a GPS satellite makes 2 orbits for every 1 rotation of the Earth. This geometry, combined with a constellation of 24 to 31 satellites in multiple orbital planes, ensures that at least 4 satellites are visible from almost any point on Earth at almost any time. 4 satellites. That's the minimum you need to calculate a 3-dimensional position. Why 4? Why not 3? Because your receiver has a clock. But it's not a perfect clock. If you had perfect timing, 3 satellites would be enough to triangulate your position in 3 dimensions. But since your clock has an error, an unknown offset, you need a 4th satellite to solve for that error simultaneously. The mathematics of GPS navigation is, at its core, the solution to a system of 4 equations with 4 unknowns, 3 spatial coordinates and 1 clock offset. Your phone does this calculation from signals received from multiple satellites, each containing a precise timestamp and a precise orbital position, in milliseconds. Every time, there is a famous story about the development of GPS that I think deserves a moment. The original GPS program, called NAV Star, which later became just GPS, was designed for military use. It would allow soldiers, aircraft, and missiles to know their precise location on Earth. When civilian GPS was first proposed, the idea of opening the system to ordinary users, there was significant military resistance. If civilians could navigate with precision, so could adversaries. So could terrorists. The compromise was a system called selective availability. The signal available to civilians was intentionally degraded. Accuracy was limited to roughly 100 meters. The full precision signal was reserved for military receivers with special decryption keys. This degraded signal was in effect for years. Then, on May 1, 2000, at midnight, President Clinton ordered selective availability to be turned off. The effect was immediate. Everywhere in the world, GPS receivers suddenly became 10 times more accurate. Overnight, civilians had been navigating to within 100 meters. Now they were navigating to within 10. The world has never been quite the same since. And finally, geostationary Earth orbit. Geo. The altitude that Clark described. The altitude where a satellite appears to hover, fixed, above a single point on the equator. 35,786 kilometers. The math behind this number is elegant. It comes directly from Kepler's third law, the relationship between the radius of an orbit and the period of revolution. If you want a period of 24 hours, the math gives you a radius of about 42,664 kilometers from the center of the Earth, which, subtracting the Earth's radius of 6,371 kilometers, gives you 35,786 kilometers above the surface. One specific altitude, one specific ring, the geostationary arc. From above, it would look like a ring of silent lights. Hundreds of spacecraft, spaced along a circle encircling the equator, each one stationary relative to the ground below. There are several remarkable things about this arc. First, it is finite. The arc is a fixed circle. You cannot add satellites to it indefinitely. As you add satellites, their signals start to interfere with each other. The International Telecommunication Union, the ITU, manages the allocation of orbital slots and frequency assignments in the geostationary arc, in a process that is part technical regulation and part international diplomacy. Getting a slot in the geostationary arc, and the frequency assignments that go with it, is enormously valuable. Nations and companies have been known to file claims for slots they have no immediate intention of using, parking regulatory rights against future need, or to trade or sell. There is a term for this: paper satellites. Regulatory filings for satellites that may never actually be built. It is a reminder that orbit is not just physics, it is property. Second, the geostationary arc has an inherent asymmetry. Because it must be above the equator. Because orbital mechanics demands it, the arc is not equally visible to everyone. From the equator, a geostationary satellite appears directly overhead. All of the arc is available. As you move toward the poles, satellites on the arc appear lower and lower in the sky. From London, at about 51 degrees north latitude, geostationary satellites appear no higher than about 28 degrees above the southern horizon. From the Arctic, Satellites in a geostationary arc are on or below the horizon. They cannot be seen at all. This is a fundamental limitation of geostationary communication. Polar regions. The Arctic, Antarctica, cannot be served by geostationary satellites. For many years, this was simply accepted. Polar regions have small populations. The trade-off seemed acceptable. It wasn't acceptable to everyone. The residents of northern Canada and Alaska, to say nothing of research stations in Antarctica, had limited or no satellite connectivity. Solutions emerged. Russia has long used an orbit called Molniya, an elliptical orbit that spends most of its time over the northern hemisphere, providing high elevation coverage to polar regions for most of the day. The US and others have used similar highly elliptical orbits for polar coverage. And now, Leo constellations, which cover the poles naturally, are beginning to fill that gap. There's one more dimension to this story that we haven't touched yet, and it is perhaps the most fascinating. What happens when satellites need to talk to each other? For most of the history of satellite communication, the answer was, they didn't. Every link went ground to satellite or satellite to ground. The ground was always in the middle. A signal from one side of the world would go up to the satellite, down to a ground station, across terrestrial networks, up to another satellite, and down again. It was a hub and spoke model. Everything flowed through the ground. This works, but it has limitations. For remote maritime routes, for areas without ground infrastructure, for coverage over the oceans, which are, after all, most of the Earth's surface. For low latency paths where routing through multiple ground hops adds unwanted delay. The solution was inter-satellite links. ISLs, direct radio, or laser links between satellites in orbit, allowing data to flow from spacecraft to spacecraft without ever touching the ground. Iridium pioneered this with radio frequency ISLs in the 1990s. Each Iridium satellite maintains connections to the satellites immediately in front of and behind it in its orbital plane, and to satellites in adjacent planes. Data hops from satellite to satellite across the constellation, reaching the nearest ground station before completing its journey. This architecture means that an Iridium phone in the middle of the Pacific Ocean doesn't need a ground station nearby. It just needs any satellite overhead, and the data will find its way home. But the really exciting development is in optical inter-satellite links. Laser communication. Light, not radio. SpaceX has equipped its latest Starlink satellites with laser ISLs, a narrow beam of infrared light precisely aimed across hundreds or thousands of kilometers of vacuum, carrying data at rates of many gigabits per second, faster than radio, far narrower beams. No frequency coordination needed with other systems. The challenge of optical ISLs is geometric. A laser beam, even a carefully controlled one, diverges as it travels. Over 1,000 kilometers, the beam has spread enough that precise pointing is essential. The satellites must track each other. Two objects moving at kilometers per second in different orbits and keep a beam perhaps a meter wide on target, over hundreds of kilometers of vacuum. The pointing accuracy required is measured in microradians, millionths of a radian, each one connected to the others by beams of laser light. And below them, 80 kilometers above the ground, the atmosphere begins. The invisible ocean of air that these signals must cross on their final descent. And here, at the bottom, you. Lying in a bed in a house, on a continent, on a planet that is almost certainly asleep. Except for you. Still listening, There is something I find deeply comforting about this story, if I'm honest with you. We built this because we needed to reach each other, not for any grand reason, not because someone wrote it into a law or declared it a priority, but because the impulse to communicate, to reduce the distance between one mind and another, is one of the most fundamental things about us. We have always built the best bridge we could between wherever we were and wherever we needed to reach. Once it was hilltop fires, then telegraph wires, then radio, then a polished metal sphere beeping in the dark above a stunned world. Now it's laser beams in space. The distances keep growing. The signals keep traveling. And somehow, we keep finding each other on the other end. If you fell asleep sometime in the middle of this, that's fine. More than fine. The signals kept traveling without you. They'll still be there when you wake up. Somewhere above you. Right now, a satellite you'll never see is doing its quiet work. Listening. Transmitting. Adjusting its antenna by fractions of a degree to stay locked on a receiver you'll never know about. Carrying a conversation, a position fix, a weather reading, a piece of someone's day. Something invisible, something extraordinary, happening above your ceiling, above the clouds, above the blue arc of the atmosphere, in the cold and perfect dark, while you sleep. The story for tonight has reached its quiet end, but your journey doesn't have to. If you find yourself lingering here, in the space between wakefulness and rest, know that there is no rush. Stay here and allow the calm to carry you forward. And if your curiosity is still softly humming, another world of quiet knowledge is waiting for you on your screen right now. Let the next story carry you a little further into the calm, until the words eventually turn into dreams.